to this second part of the afternoon session. We have the pleasure of having our afternoon session plenary speaker, Professor Sukumar, and his talk is entitled Scaled Boundary Cubature Scheme for Numerical Integration over Planar Regions with Affine and Curved Boundaries. Please.
Okay, thank you, Eduardo, for the introduction. Oops, let me go back. And to the organizers for this invite. So as was mentioned, the title of my talk is Scaled Boundary Cubature Scheme for Integration over Planar Regions or two-dimensional regions with affine and curved boundaries. This is joint work with Eric Chin, who's at Livermore National Lab, and you can see the campus below of the lab. And so the entire talk is based on this paper, which appeared earlier this year in CMAME. So you can pretty much follow the talk and the paper. They are in sync. Okay, so we based on the, especially on VEM and DG and other methods, we have realized that, numerical integration arises over polygons and polyhedra in general. And there are different types of polyhedra and polygons that can arise. And the question is how to do integration on this game, on these shapes. Because both in embedded or fictitious domain methods, one tries to simplify the notion of approximation spaces by using rectangular elements, so to speak. But then you have these cut cells which arise where you need to carry numerical integration. So the difficulty is transferred from approximation spaces to numerical integration on one hand. And even in VEM, for example, you bypass the notion of constructing basis functions, but still there could be challenges arising which on complicated shapes and furthermore, even in DG, for example, then it makes it really interesting to apply numerical integration schemes on those shapes. So the question is, okay, on these shapes, how do you carry out numerical integration of polynomials, non-polynomials, and also even possibly weakly singular functions efficiently and accurately. So my emphasis is more on accuracy because typically such elements, if they arise, would only be a small sample of the entire mesh if you do a cut cell method, for instance. So anyway, so I already mentioned some of these methods, but I'll just go through it again. So we have VEM and DG, and many talks in this workshop are on this topic. And polygonal and polyhedral FEM methods, where it came from, all those efforts in this direction. And I mentioned XM, where you can have cracks and holes, and you end up with these polygonal shapes where you have to do integration over these shapes. So you want something efficient and robust because the approximation spaces, because of enrichment, are very accurate. So if you want to get optimal convergence, then you must ensure that the integration also is sufficiently accurate so that the convergence rate is recovered. And domain decomposition and also contact. And contact is one area which in fact, Eric is exploring higher order contact in some mechanics codes at Livermore right now. And the last thing I mentioned before is on fictitious domain or immersed boundary methods, where you take a simple Cartesian mesh and you hit your geometry with it. And then the issues of imposing boundary conditions and numerical integration arises. So therefore, these cut cell methods also can leverage these integration schemes. So that's the setting. So the outline of the talk is I'll go through what is known as the scale boundary parametrization, which has been around for like 20 years or more. And then I'll look at the same parametrization and show how it can be applied for numerical cubature or integration over planar regions. And two simplifications I'll show you. One is for what happens when the integrand is a homogeneous function, so a sum of polynomials or even other functions. And the second case, that's over basically polygons. And we'll also look at curved polygons. So there's a lot of interest right now on VEM for curved elements, so it might be relevant there. And I'll show you how it reduces to formulas which we have derived before. And in fact, we came to this parametrization not the direct way, but from the inverse way, literally. And that's how I'll show you that when we get to the homogeneous function simplifications. And two things that are relevant are how do you integrate efficiently and accurately weakly singular functions that have finite energy, but where there's a singularity either at a vertex or inside the element itself. Because you want to get rid of the singularity, and also we can handle weak, nearly singular functions, because sometimes when you even knock off the singularity, there could be adjacent elements where the functions could be still nearly singular because the gradients are very large. And so I'll close with a bunch of numerical examples, which are basically taken from the paper, but the first 4 topics are essentially the half of the talk, which should cover the formulation and where and how one can apply this technique. And before concluding, I'll also show you a 3-dimensional example. So we want to explore this in 3 dimensions eventually. So we can also apply this in 3 dimensions, and I'll show you a slide on the extension to 3D, at least some initial results. Okay, so let's begin. So we take a domain omega. Now we consider that it is composed of, the boundary is composed of both affine segments and also curved boundaries, which are parametrized, which have a parametrization. So C1, C2, C3, C4, C5, C6. And for each part, T goes from 0 to 1. And the vertices are V1, V2, V3 up to V6 again. And we assume that Ci of 0 for every segment or every subset, that Ci0 is equal to Vi, and then Ci1 is the next vertex, Vi plus 1. So that's the statement. So this is V3 to V4, then V4 to V5, and so on. And T goes from 0 to 1 here, 0 to 1 here. So that's the parametrization, which is given here. So as I was mentioning before, if someone has a question, they can just stop me. So it's perfectly fine, rather than wait at the end, because you want to clarify, right? When I speak itself, or on that slide, if you have a clarification, it might be good to clarify it there itself. Okay, so then what one does in the scale boundary parametrization is you pick a point x0. It can be inside or outside. So that's the nice part about this. It will still work. So you pick the scaling, what is called a scaling center in the context of scaled boundary. But here is just a reference point in the context of our scheme itself. So x0 is a point inside. And then you just join it to the vertices. So it need not be star-convex. If it is star-convex, it so happens that if the point x0 is star-convex, then you can actually get a quadrature scheme that has positive weights inside also. If not, if it's not also star-convex, then you can still get a quadrature scheme that is accurate, but of course it will consist of positive and negative contributions. So here you have this T1 to T6 as the sub-partitions, and then the entire domain omega is the union of these 6 pieces. Okay, so if you take any arbitrary sort of, here I'm showing you a triangle instead of a curved triangle. So the parametrization phi is 0 to 1 to this T shape, and the parametrization is given by x0 plus psi times C of T minus x0. So here x0 is this reference point, which will come up inside, and psi goes from 0 to 1. So let me, oops. So psi goes from 0 to 1. So you can see at the location x0, psi is 0. Then there are these isolines. And on the boundary, psi is equal to 1. So that's how it goes. So that's the mapping here. And in the psi direction, and likewise in the t direction, it goes from one end where t is equal to 0 to the other end when t is equal to 1. So that's the whole parametrization of this. And that's, you can see that basically maps to a square, 0, 1 square. So this was done actually, more than 24 years ago by Song and Wools. They used it to what is called the scaled boundary finite element method, what they called. It was a semi-analytical method to solve partial differential equations. And it's been developed a lot more in the past 10 years, I would say, moreover. So they call this as a scaling coordinate, psi, essentially, and they chose x0 to be 0. So there the parametrization was just x psi times ct, because they chose this point to be the origin, so to speak, of their element, and then they scaled from there, because it's like a parent element, so to speak, in their context. But here we're not using that, we're just using it for integration. And there'll be another issue which arises on the mapping itself. Okay, so let's start off. So we have a function f. We want to integrate over every piece t. So we'll introduce this parametrization. which goes from 0, 1 squared to the domain, which is shown here in blue. And now I can just take this function f and apply this mapping here. So you get this composition f over phi of psi and t now. And then you get a determinant of the Jacobian. So determinant of the Jacobian is this. And you can see from here, if you take the partial of this with respect to psi, you get a ct minus x naught term. And if you take a partial with respect to t, you'll get a psi times c prime t. So the tangent vector will appear. So when you expand this out, you can also write it as psi times ct minus x naught dotted with c prime perp t, where c prime perp is the vector in the normal direction. That is, it is basically c prime rotated by 90 degrees. Another way to view this is, which will appear, I think, in the next slide, is to look at these two terms together is essentially like the determinant of this and c prime itself, or it turns out to be twice the area enclosed by this, or the two-dimensional absolute value of the two-dimensional cross product, if you want another interpretation. So let's see that now. Let's see what happens here. So I just reproduced what I had before. So essentially, we have done the transformation. Oops, no, I went back too much. Yeah, so this is essentially the transformation. That's the main result, and there's nothing much more to it really. In converting an integral, which is over the so-called triangle here, or it can be any curved triangle or any curved shape, to basically an integral over a square, right? So 0 to 1, 0 to 1. So we have basically attained this transformation. But of course, there are these, the curve parameter c is there, and c prime perp is there, and so on, right? And of course, the composite mapping FO phi, right? So that's what I've reproduced here above. And now let's look at a few things, right, which makes it interesting. So let's assume that first f is a degree q polynomial, that we know it's a polynomial, but of course we don't know its explicit form. And let's assume that ct is a degree p polynomial curve, right? So if ct is a polynomial, is just an affine segment, it's a degree 1 polynomial curve. If not, it could be a NURBS curve or a Bezier curve in general, right? So we'll notice that the integrand will still be polynomial, because the mapping, going back to my previous slide, so the mapping is linear in psi itself. And if c itself is a polynomial, then the mapping also will be polynomial in c, right? So therefore, we see that if c is a polynomial, then it'll be degree q plus 1 over, because you have a psi here, and this is written the same degree as psi itself. So therefore, this will be degree q plus 1. And then it'll be degree t will be pq, because this is degree p, this is degree q. So therefore, pq plus 2p minus 1. So that's what appears here, because you have a product of the c which appears here and a c prime perp. So c prime perp is p minus 1, and this guy is p. So p plus p minus 1 is 2p minus 1. So that's how you get this degree. So the degree is elevated slightly, but the nice thing is that you still retain the polynomial. The mapping does not destroy the polynomial integrand. So we can apply basically tensor product rules over this shape, and therefore you'll recover the optimal convergence rate, or you get exact integration using Gauss quadrature. So as I mentioned to you before, you can also interpret this as twice the area of a region. And that's what is shown here on the right. So this is c prime t here, and the normal is in this direction. This is ct minus x naught. And therefore, you can think of this 2a, which will appear again afterwards, as ct minus x naught dotted with this perp, or the determinant of this, comma, c prime t. So therefore, in the specific case when ct is affine, so if you have basically a triangle, then you get the simplified expression, because you can get rid of this term. The ct minus this gets modified into just a constant, right? A constant 2a naught, 2a t, which comes out, and then you're left only with psi, d psi, dt, and the composition here, f colon psi, phi. Okay, so if there are any questions, you can ask me, or I can just proceed. Okay. Okay, so as I mentioned to you before, we can decompose the integral into a union of integrals, and that's what is shown here. So here you have three triangles which are shown here. So that's the first part. So you get, so this expression comes from the previous slide where I showed you. And the remaining three are going to be curved triangles, which are parametrized by C4, C5, and C6. And here, of course, I don't know, it depends on what is Ci of t and what is this expression. And then there'll be further simplifications that can be done, of course. But here, this is simplified because this term, as I told you in the last slide, becomes 2 times the area. Therefore, this comes out of the integral. Okay, so let's see some two simplifications for Q homogeneous functions. So we'll choose a Q homogeneous function and we'll choose the center to be the origin. So if that is the case, then this composition is also Q homogeneous with respect to psi, because psi varies linearly. So you can see here psi varies linearly. So if phi itself is Q homogeneous, then FO phi will also be Q homogeneous with respect to psi. So then we can apply Euler's homogeneous function theorem, which says basically, think of this as basically QF. So QF is equal to partial of f with respect to psi times psi. So that is essentially in one dimensional what is the homogeneous function theorem. So what this brings you is that if you take the chain rule, so you take del by del psi of this composition times psi square, you can write this as the product rule. So first term is partial of this times psi square plus this times partial of this, which is 2 psi. So that's the product rule which you obtain. And now you can see that this is basically 2 plus q FO phi psi t psi. So where I've used basically this relationship here. So this guy is basically, so one psi goes off with this. So you get del by del psi of psi is equal to q psi, is equal to q basically, right? QF. So therefore you end up with this 2 plus q of this composition times psi by basically getting rid of this by using this. So that's one way of looking at it. And the second is, so this actually, I don't think one of my, I had a marker below that, probably it's getting blocked. So anyway, so that's the first simplification. And this, it turns out that this is basically the Euler's homogeneous function theorem. And then let's now see what happens in this context, right? So this is the Euler's homogeneous, the reduction which I showed you from the previous slide. And now let's go back to our formula over triangles. So you recall I had a specific formula when the domain is a triangle and not a curved triangle. So this 2a comes outside. So now I can use equation 1 to basically replace this term, right? So in this term, I can replace it by 2a area divided by 2 plus q. So I can basically get this guy out. So 2 plus q, I can replace this by del psi of f psi square from the left-hand side. So I'm just replacing this part. So I'm just replacing this part with this here. So d psi dt. Now we have basically the fundamental theorem of calculus. I can basically integrate this. So to f of phi and 1 psi, 1t, because psi is equal to 1 on the boundary and psi is equal to 0 on the lower boundary. So therefore that goes off. So you get f of phi 1 comma t dt. And this becomes basically FOC t, because 1t is basically the boundary, right? When psi is equal to 1, we are on the boundary. So this becomes a one-dimensional integration because phi of 1t is equal to ct. So this is a one-dimensional integration, and this is basically equivalent to the HNI scheme, which we did many years ago. So in fact, we got to this sort of radial, this sort of scale boundary by the inverse method, by basically starting with this and seeing, okay, how is this? There must be a two-dimensional integral, which basically is coming from where this comes from, and that's what happened essentially. So when you do the reverse process, you end up with the scale boundary. Oh, if you use the scale boundary parametrization, this is a specific instance of that formulation. Okay, so let's see the next case of a curved triangle. So the same steps here, but now we basically need to, again, apply this, because on the psi direction, we can get rid of it again. And essentially the same steps, but now just C and C prime perp are left behind when you apply the fundamental theorem of calculus, and you're left with this essentially. And this is again equivalent to the same scheme. where we had applied it for curved, basically, polygons. And that's in this IGNME paper. Okay, so the next step is how to look at weakly singular functions. So we could have, let's assume that you have a singularity of order beta, where beta is between 0 to 2 in 2 dimensions. So it has finite energy, so it's basically an H1. And now you want to integrate this. Of course, if you use standard Gauss quadrature, it'll be very inaccurate. So we introduce this scale boundary parametrization and just go through the same steps as before. And you end up, since we have so we introduce phi is equal to xc plus, so we choose x naught to be xc in this case. So x minus xc here becomes psi times ct minus xc. So you get a psi raised to beta in the denominator, and that goes up to become psi raised to minus beta, and you're left with this, of course. So what we notice is that if beta is equal to 1, so if you have a power of 1 here, then this vanishes, right? So this goes off. So there's no psi singularity that goes away. So the psi singularity is eliminated if beta is equal to 1. And if you're basically on an edge, which is parameterized by an affine function in T, then this matches what is known as a Duffy transformation, which takes in, which maps basically a triangle to a square in 2 dimensions. Okay, so what happens when beta is not equal to 1? Then the convergence with the parametrization will be poor because it's only tailored towards beta is equal to 1. So then we just go to a generalized SB parametrization where we just raise this to the power of alpha and go through the same exercise of finding out the Jacobian, the determinant of the Jacobian, and going through the algebra. So now we find that if the exponent of psi is alpha into 2 minus beta minus 1. So if this exponent is a polynomial, it's an integer, a positive integer, 1 or more, then this guy basically becomes a polynomial power of psi. So that therefore it can be taken care of by Gauss quadrature. So we'll choose the smallest alpha. And again, if it's an affine, it's basically a triangle and x naught is equal to 0. This matches what is known as what we call the generalized Duffy transformation in this paper, right? And the other option is to actually use Gauss-Jacobi rule, which is in fact most efficient because those rules are tailored towards a singularity. So you can take any power of beta and essentially it'll take care of that exponent there precisely by knowing the value of beta, the exponent of what appears there. Okay, so that's the first step. So we notice that even if you have got rid of psi, because it's in one direction, we can either use this generalized transformation we proposed, or you can use the Gauss-Jacobi quadrature. But we are still left with this other term, which is ct minus xc raised to beta. And you can take a triangle, for instance, here. You can skip, I'll skip the derivation here, but it's just the basic steps here, where if xc is the singularity, but xc is very close to this edge, then in the neighboring element, there could be still basically an issue of how do you do the integration accurately, right? Therefore, even on this edge, there'll be basically a near singularity which arises, and that's what needs to be taken care of. You apply basically we apply the transformations, and you end up with this integral here, and again this integral here, which is L square plus tau square. So when L is very, very small, there could be still a near singularity which arises in the previous picture which I showed. Then we resort to how do you basically stretch it out? So essentially the idea is to stretch it out, and that goes back to the work of Ma and Kamiya in engineering boundary analysis and boundary elements. So they used this first beta equal to 1 way to get rid of it by posing this as a total differential and then integrating it out, right? You can get exact values of the forward and the backward map through these formulas for beta equal to 1, 2, 3. So it might have been better to just call this something else. You can think of this as a gamma. For only integer values, you can get explicit solutions here, right? But not otherwise. So let's look at some examples. So we have polynomials over polygons first to start with. So now we choose 2 choices. As I mentioned to you before, you can choose the origin or you can choose the vertex average. So the point can be inside the polygon or outside the polygon. So the integration still works, and you don't need to do any other simplifications or any pre-processing steps. So here's shown the steps, the quadrature points for when x naught is equal to 0. And here is when x naught is equal to the vertex average. So you can see here that we are using 2 points on the boundary, and 3 points in the psi direction. So 2 points in the t direction and 3 points in the psi direction over every triangle. So therefore 6 points you can think of for every triangle. So this is a 7-sided septagon, so 42 points in this case, right, which is observed. So we are somewhere here, right? So 3 points in the psi direction and 2 points in the t direction. So it can integrate a polynomial of degree 3. So if you want to construct this cubature rule, and if you're going to repeatedly use it, then of course it might make sense to save this quadrature rule. But if you're just doing it once, then of course there's no point in saving it and then recomputing it. You can just recompute it on the fly. So a polynomial of degree 3 will be exactly integrated by this scheme if you use this rule here, right? So of course, what I showed you before in terms of the theory, it matches the expected number of points to get basically machine precision accuracy. So let's take a few more tests which are more general, and the very popular sort of test functions for scattered data approximation are from Franke in this tech report here. And the first function is like a sum of Gaussians. I just showed you here. The second is a tan, and the third is a rational function. Or, I mean, it's a cosine on top, but a polynomial on the bottom. The first one is very popular. It's got basically valleys and peaks and valleys. So you can see these 3 bumps here of the Gaussians. So it's basically the sum of 4 terms here, and you can see 3 basically different bumps here. So these are more challenging functions to integrate in general. So we integrated over 4 shapes, and what we do is we take these shapes and basically we map it inside the unit square so that it sort of mimics the test which Franke did. And here I'm showing you the iso contours, but they're very difficult to really visualize here. So the 4 shapes are overlaid here as well as their iso contours. And these are the shapes which are in the physical space. And here are the results, which I just shown you here, and they compared with this Green-Gauss theorem of cubature scheme of Somariva and Vianello. So we can see that both our schemes are approximately the same in terms of accuracy and the number of cubature points needed. But of course, we don't need to do any pre-processing, and we don't have to know the antiderivatives or numerically compute all those terms, right? We get it in one shot. And besides polygons, we also can do, of course, curve shapes in this context. The same formulas can be applied. Okay, so now we also wanted to do a quick comparison of what is the time to generate these integration rules over polygons. So we can inscribe polygons of different number of edges inside a circle, and we compare it to constrained Delaunay triangulation, where you construct the triangulation and then use triangular quadrature rules and also Gauss green. So there are these 3 different sets of results. So the top result is basically for Delaunay, then is the green Gauss, and then the bottom is ours, right, basically. So what we have done here is just by normalizing everything to the number of cubature points per edge. So if you have 1,000 edges, then the number of cubature points is normalized with respect to that, right, number of edges. And of course, you can keep on increasing the degree of polynomial that is integrated inside this polygon with many, many edges. And so we find that because of the less overhead, we are about 50% faster than green Gauss and 90% faster because there's no meshing required at all, right, in the scheme itself. So then we can move on to curved regions. And again, you were taking some standard test, a constant function, one of the Franke functions, and we combine an exponential and trigonometric function. And we use different choices for x naught, either at the mean vertex coordinate, or it could be also at the center. Here I'm showing you the mean coordinate. So if we are taking different curved shapes, these are basically, I think they are cubic Bezier curves, 4 of them put together, and we want to integrate a constant, a 5th order polynomial, a Franke function, exponential, right? So clearly, of course, for a constant, for the first 2 cases, we barely need any, the number of points is very low, but as the functions get more complicated, you need more points per edge, of course. And that's what is observed in all cases. And it gets more tougher, of course, for this function, especially in the t direction, as you can see from here, because of the fact that there's a singularity, because the shape itself is not regular, right? So therefore, there's a cusp here. So therefore, you can see there are more points needed in the t direction there. So the next test is this integrating singular functions with the side transformation, or they should be S3 and S4. So they have 4 different functions. So this guy has a power of r to the power of 1/2. So this is x squared plus y squared square root divided by 1/2. And then this is 9/5. So this is a different power. This is half, and this is 9/5. So therefore, these are not beta equal to 1, 2, 3, essentially. They're different values. So, so then we take a very skinny triangle, sort of a well-shaped triangle, and a triangle with a curved side, and we compare with no transformation, the SBC rule, or Gauss-Jacobi transformation, or Gauss-Jacobi quadrature rule. So again, we can see that the take-home message is, of course, if you don't do any transformation, you can barely get to -5, even for the simple functions. And in fact, if the function gets more complicated, like the Franke functions, you're stuck at like -1 or even order 1 error, essentially, as you increase the number of points. So whereas with Gauss generalized SB or even Gauss Jacobi, it's more efficient, and you can see that Gauss Jacobi is the most efficient in general because it explicitly gives you, you're constructing a priori a quadrature rule that takes care of the singularity in the psi direction. And then now we do apply the T transformation on the shapes, same shapes, but now take a even more sort of almost like a sliver triangle so that it becomes, the near singularity becomes even more pronounced. And we use just gamma equal to 1, gamma equal to 2, and gamma equal to 3 if you want, so that it's not confused with the beta power here, which is half and 9/5. And again, we find that our results, at least based on this, even though this is not optimal, so we use basically beta equal to 1, 2, and 3 here, that we're able to basically get close to machine precision as you increase the number of quadrature rules. We have also applied it to Wachspress basis functions, and we can eventually show that, okay, they're compatible to Green-Gauss and also the triangular quadrature rule, but we don't require the overhead of actually doing any pre-processing. And it, of course, requires many, many points to integrate, if you want to get machine precision. But given the approximation errors probably at best here, these number of, say, 10 points on the quads and 10 by 10 and say 15 by 15 or 20 by 20 will get you that accuracy, even if you want 10 raised to -5 or -6 accuracy on these shapes. And the next result is on XFEM, where we emphasize that you can get near singularities. So if you have a singularity at this point XC, then clearly inside this element there's a singularity. But even for this element on the boundary, if this delta X is very small, then it influences the integration on this element also when you compute the stiffness matrix entries. So these are positive integrals and negative integrals, which are shown. And then we basically compute these entries in the stiffness matrix for different values. So all the entries are computed. So there's a bar basically of the error. So for different values of delta X, you can see the performance. So it basically is robust with respect to delta X. And the last example is on transfinite mean value interpolation. So this is something coming from generalized barycentric coordinates, is how do you interpolate an extension of barycentric coordinates is how do you interpolate over curved shapes, right? If you want to get a transfinite interpolant, was done initially by Mike Floater and Dyken and Floater in this paper. So basically you have a kernel function. So the weight function becomes now an integral of a kernel function, which goes as 1 by cubed in the transform domain. And this was closely related to what are called LP distance fields, which was done by, I think the reference is here, Belyaev, where they show that you can actually generalize this notion of distance functions to LP fields. And what the remarkable property which I did not mention is that the weight function in the mean value coordinate, or the reciprocal of the weight function in the mean value coordinate, is like an approximate distance function to the boundary of the domain. So you have this egg-shaped domain. So the reciprocal of the weight function is like an approximate distance function. So it is identically 0 on W on this curve, and it is strictly positive inside. So we know that W must be strictly positive for the polygon because you're normalizing it, right? So this is basically a summation for the polygon, and you're normalizing it by the sum of the weights. So for a polygon, the sum of the weights is basically positive at every point inside the domain, and it's basically just the inverse of that is basically identically equal to 0. Inverse of W is identically equal to 0 on the boundary. So what Belyaev et al. Showed is that as P goes larger and larger, this gets a better and better approximation of the exact distance function, where you have to actually solve the Eikenol equation if you want to get the exact distance function. But there's an approximate, and what we did was to just see, okay, can we, if we use this formula, can we approximate the L2 error by doing the integration over this shape here, because it's parametrized by something here, and see if we can, at least it shows that our method is accurate. So we compute the L2 error using SBC, And you can see that as p is equal to 1 to 10 to 100, it approximates the exact distance better. So you get -2, approximately 10 raised to -2 error for p equal to 100. And we compute the exact distance function here using a Newton's method to get the exact solution. So it's accurate to machine precision. So the last slide is the extension to 3D. So whatever I've shown you sort of generalizes to 3D. So now you think of this. So C of is a parameter in parameter space. It's a function of u and v. So C of u and v minus x naught. So in 2 dimensions, it was C of t essentially. Now C of u and v is a surface describing the boundary of the region of an integration. So on polyhedra, you can apply it recursively, and you basically recover this formula. So it becomes, instead of the area, you get a volume, and then this composition here, and you get a psi squared terms times u d psi du dv. So that's what is d. So you have a 3-dimensional integral now, where this is the volume of the tetrahedra formed by vertices x naught. You take a point on the face. Typically, you would choose, in fact, one of the vertices, and which is other than the edge of interest. So you join those 3, which form a triangle, and you connect it to a point inside, which is x naught. For example, the centroid of the, or the vertex average of all the nodes in your polyhedron. So here's an interesting polyhedral, which is called the Selassie polyhedron. So it consists of sort of hexagon faces, 7 of them. So it has 7 faces. It has 14 edges, 14 vertices, and 21 edges. And the interesting property of this is that it has a face, essentially it has a face whose edge is connected to every face. So there is an edge of every, so every face's edge is connected to every face in some sense, right? So this is the only property of this polyhedron and of the tetrahedron. So if you take a tetrahedron, then you can see that basically if you take any face of a tetrahedron, its edges basically can be connected to all the other faces. So that's what is obtained here also, remarkably. So of course, there's non-convex. So here we use x naught is equal to 0, and you just take a 3×3 rule here just to show that the quadrature points here, and also a 3×3 rule here where x naught is now at the vertex shown here, right? So you can again integrate arbitrary polygons over, or arbitrary polynomials over these shapes, which are polyhedron in general. So that makes it more efficient. And we compare this, actually, we compared it to our work in a recent CAGD paper where we did basically homogeneous numerical integration over 3-dimensional polyhedra. Okay, so let me conclude. So what I've done in this talk is to give you a flavor of the scale boundary cubature scheme, which is where the accuracy is on par with other schemes such as Gauss green. The rule is fast because of the simplicity of the form of the transformation. And of course, we got to this from an inverse method, but of course, when you apply it, you just apply the scale boundary transformation and off you go, essentially. Apply the change, basically apply the Jacobian transformation and find out the integrand, and then just apply the tensor product rule on that. The implementation is simple. Positive weights and points are inside the domain if you have a star-convex domain. And the flexibility it has over other schemes is that you can apply non-convex polygons in polyhedra. We hope to in the future. And in 2 dimensions, we've shown that you can apply to curved regions, and also non-simple regions, which could be intersecting also. And we at least looked into how do you construct, at least how do you get efficient and accurate, more so, integrals for computation of integrals for weakly singular functions that have finite energy, with both the singularity canceling approach in the psi direction and also the handling the near singularities which arise in the t direction. And in the whole motivation was that it can be applied to many different schemes where you have polygonal elements underlying the method itself, as in VEM or DG, or you could generate polygonal elements because of the cut cells in cut FEM or XFEM or other methods. And also many of the ideas can be applied to BEM, of course, also. And the extension to 3 dimensions I mentioned before, and Eric is also exploring applications in higher order computational contact when you have curves, basically interfaces, and you want to apply contact between 2 solids, for example. So, okay, so that's the talk, and I'll stop here. Thanks.